Hi guys. Oh, sorry. So my name is Enrico Bottazzi, and today I'm going to introduce you to Multilateral Trade Credit Set-off in MPC, which is an application of MPC. And this is a work joined with my colleagues and fellow researcher Nam and Masato, which are also part of the PSC team inside the Ethereum Foundation. So let's jump into that. First of all, I want to introduce you the concept of a payment network. So as you can see here, the payment network involves 3 firms. Each firm has a balance, and each arrow in this graph represents an obligation, like some amount of money that a firm owes to another. And the problem of this payment network is that they are kind of stuck because each firm, given their balance, they cannot pay another firm. So for example, firm 1 cannot pay firm 2 because they are waiting firm 3 to pay themselves. And the same goes for the other 2 firms. And apparently, the only way to solve this problem is to use external liquidity, which we know that is expensive. But actually, there's another solution to solve this problem, which is multilateral trade credit set-off. And we can see how we apply that from the figure on the left to the figure on the right. And you can also intuitively understand this thinking about, like, if you owe money to your friend Alice, Alice owes money to your friend Bob, and Bob owes you money, you don't need to make 3 payments to settle everything. You can just remove the debt from the system. And another example that might help people understanding it is how the application Splitwise works. So what we achieved is a way to remove obligation from a payment network without leveraging expensive external injection of liquidity. So this is an example of multilateral trade credit set-off on a bigger scale applied on the network in Sardinia, in Italy. And the cool thing that you can see is that the more are the firms participating in it, the bigger, the higher the chance to detect these cycles of credit and debt, and therefore the greater are the liquidity savings for the firms involved into the payment network. So this is actually something that exists in the real world. Like the flag that you see on the top right is the one of Slovenia, a country in Europe. And this is how the process works. So the firms that decide to join the system will send their credit data to this third-party agency managed by the government. And this agency will reconstruct the graph, perform this set-off, so remove these cycles, and return the updated data to the firms. While it works in practice, there's a very low participation rate, and this leads us to our research thesis. We believe that the limited participation is due to the fact that these firms have basically to give up all the information, the view on their sensitive trade credit data to this government agency. And we also believe that if we could build this same system with privacy embedded into that, the participation will be higher, and this will also yield, as we said before, greater and higher liquidity savings for the firms involved in the system. So what do we mean by privacy? First of all, we want to hide the balances of the firms. We want to hide the amount of each obligation, and we also want to hide the topology of this payment network. So in practice, it means that we also do not want to reveal the fact that there's a specific obligation between 2 firms in this network. And how does this work? We basically replace, like before you had like the government agency there. Now this is replaced by a set of MPC servers that are able to perform this operation somehow obliviously. So unfortunately, I don't have time to go through like the details of MPC and the algorithm that we construct, but I want just to bring the most significant results of our research. So we were able to significantly reduce the asymptotic complexity of this algorithm to be performed in an MPC environment. And we did that mostly through 2 techniques. One is secure graph anonymization that allows these servers, these multi-party nodes, to anonymize the graph before opening its shape. And the second contribution is the secure network simplex, which is a network flow algorithm, and we built its corresponding and efficient version in MPC. So we are going to publish a paper related to what I described soon, and you can check my blog to be notified, or also follow me on Twitter to see the result published. Thanks for your attention.
Thank you, Enrico. Anyone has any questions? Raise your hand, I can see you, and I can throw this to you, hopefully. Okay, this one's close.
All right. My question is, what happens if party one has a higher interest rate than party two? Is that able to factor in interest rates?
Yeah, we didn't get into this part, basically. So we are just tackling this problem from a cryptographic perspective, not getting too much into the details of the process.
Hey, great use case. How do you do can you touch a bit the secure graph anonymization? Like, are you using something like an oblivious RAM? Like, what's the actual MPC technique to anonymize the connections?
Yes, so basically for that we borrow a technique from this field in academia that is called graph anonymization, that is not related to cryptography. And this is mostly used by, like when a company, for example, wants to open source some graph, but they also want to hide the data behind the graph. What they do is they use like this kind of obfuscation or perturbation technique to the graph. And for example, we use a technique that is very simple. It's called like random add and deletion. So you basically just randomly add some edge in the graph and randomly delete some edge in the graph. And what you get out of that is a new graph, which basically like the entropy generated by this mechanism is high enough such that you cannot infer information from that. So I guess that it's also correct to mention the trade-off, because since we are also deleting edge, we are somehow sacrificing some of the optimality in the algorithm, because basically some obligation will disappear. But I think this is a trade-off that we are willing to accept.
We have one more question left. 1 minute.
Thank you. Does it relate to blockchain in some possible applications?
No.
Not yet?
Oh, maybe one more. Oh, there's a question at the front. There's a lady here. Oh, sorry.
Thank you. Yeah, thank you for the talk. So basically, it creates an equivalent graph from the initial graph, and then what happens after that? It's being reconstructed, and it looks like the algorithms that you described is basically like AC encryption, where some rows being perturbated and then switched with each other or something like this. So there's supposed to be a key by which you can revert the procedure and then do something with it, or?
Yes. So I have 7 seconds. Like the idea is that after the graph is anonymized, these parties of the MPC will have an open version of the graph that doesn't really conceive any meaningful information. And what they will do from then, they will perform this algorithm, which specifically is about like solving the minimum cost flow problem over this graph in a MPC, like linear secret sharing way. So it basically means that all the values that are part of this graph are split between parties. So every time they do, I don't know, an addition, a multiplication, or a comparison between secret share value, they will also get, as a result, another secret share value. And in order to reconstruct this value, in order to see what's behind the real data, basically all these parties need to collude and recompose the value from the shares. So that's how we guarantee the privacy, basically.
Oh, we have time for one more question.
So the results are is a chain of liquidations, right? So can this result be used to reconstruct the initial debts? So, for example, if I get 100 liquidated and my friend also gets 100 liquidated and another friend gets 100 liquidated, that means that there were some relations between us, and people could just use this to reconstruct the original debts which we want to hide.
Yes, that's true. I mean, like one of the assumptions that we make in this construction is that the firm itself are not malicious. So a firm is interested in protecting their own data, and they are not trying to collude with other firms to fetch, like, I don't know, some intermediary party in this cycle. And what I would argue is that they could do this anyway, even without this system. So it's not that we are trying to solve the problem of a firm not being able to see if there's some intermediary party between themselves. So probably I didn't explain it very well, but like in our, let's say, threat model, we don't consider the firms as a potential attacker. We only consider this MPC server as a potential attacker that tries to fetch information from this graph.
Okay, thank you.